Good morning, Dr. Cock and friends. Today I'm presenting constructing heuristics for the eco-friendly garden challenge, a computational thinking approach. In the 21st century, math is no longer about rote memorization. It is about becoming strategic problem solvers. I have selected a non-routine optimization challenge that requires more than just a formula. It requires a logical roadmap or a heuristic. I like to call computational thinking the grammar of mathematics. Just a grammar structures a language. CT provides the framework to turn complex problems into systematic solvable steps. In this presentation, I will demonstrate how the 6 components of CT empower students to maximize resources and make evidence-based decisions. Let's explore how logic transforms a simple garden into a masterclass in mathematical optimization. Before we dive into the garden, we must define what a non-routine problem is. In mathematics, these are problems that have no immediate or obvious solution. Unlike routine exercise, there is no single formula to follow. These problems are characterized by their complexity and higher order thinking requirements. They mimic the messy reality of daily life, where resources are limited and we are forced to analyze, evaluate, and create our own strategies. Essentially, a non-routine problem transforms a student from a passive learner into an active investigator. To understand the difference, let's compare two scenarios. In a routine problem, a student might be asked, calculate the area of a rectangular garden with a length of 10 meters and a width of 8 meters. This is a simple calculation using a memorized formula. However, in our non-routine problem today, the challenge is given 36 meters of fencing. What is the largest possible garden area you can build? Here, there is no immediate formula to find the answer. Students must investigate, test different combinations, and construct their own strategy. This is the shift from just calculating to true problem solving. The problem I have selected is the Smart Garden Planner. Imagine a school wants to build a vegetable garden to promote sustainability, but they have a fixed budget, only enough for 36 meters of fencing. The question is, how do we arrange this fence to get the maximum planting space? This problem is highly relevant to 21st century learning because it teaches resources management. Students learn that in the real world, we must maximize our output while working within limited constraints. Now, let's apply the first component of CT, decomposition. A 36-meter fence seems like a big challenge, so I broke it down into a smaller part, manageable parts. First, I identified the main constraint. The perimeter is fixed at 36 meters. I then simplified the formula to bracket L plus W equals to 36. And then 36 divided by 2, we got L plus W equals to 18. By doing this, the complex task of designing a garden becomes a simple search for two numbers that add up to 18. This reduction makes the problem much less overwhelming for students. Moving on to pattern recognition. This is where we look for trends to simplify our work. As I tested different dimensions, starting from a very thin 17 meter by 1 meter rectangle, I noticed the area was only 17 meters square. But as the length and width values moved closer to each other, the area began to climb significantly. I recognized a vital mathematical pattern. The closer a rectangle moves toward becoming a square, the larger the area it encloses for the same perimeter. Recognizing this pattern acts as a strategic shortcut, allowing students to predict where the maximum area will be without calculating every single possibility. Now we move to the abstraction. This phase is all about filtering the noise. In a classroom setting, students often get distracted by unnecessary details like what vegetables they want to plant, or what color the fence should be. As part of my heuristic construction, I encourage students to strip away all these visual distractions. We shift our focus entirely to the mathematical skeleton of the problem. Instead of looking at a garden, we look at a formula to bracket L plus W equals to 36, which we then simplify to L plus W equals to 18. The benefit here is clarity. By focusing only on the numbers that affect the budget and the area, students can solve the problem more efficiently without cognitive overload. This is a crucial skill in computational thinking, learning what to ignore so we can solve what matters. Now we move to the heart of the solution, algorithmic design. Instead of using trial and error or guessing, I have constructed a systematic step-by-step plan that guarantees the best result. First, we start small. We set the width at 1 meter. Since we know L plus W must be 18, the length becomes 17 meters, giving us an area of 17 meters square. Then we iterate. We increase the width by 1 meter and repeat the calculations. We record every result in a table. This allows us to visualize the data and see how the area changes. Fourth, as we go, we analyze the numbers. We look for the turning point, the exact moment where the area stops increasing and starts to decrease. Finally, we select the winning dimensions, the ones that provide the absolute highest area value. By following this algorithm, we transform a complex optimization problem into a logical and repeatable process. It ensures no stone is left unturned, and every student can reach the same successful conclusion. Now, we move to logical reasoning, where we must justify our choice using the evidence we gathered. It is not enough to just find a number. We must prove why it is the best solution. Look at the comparison. If we choose a 10 meter by 8 meter garden, we get an area of 80 meters square. However, if we shift just 1 meter to a 9 meter times 9 meter garden, the area increases to 81 meters square. The logic here is powerful. Since the perimeter remains exactly the same at 36 meters, the 9 meter times 9 meter garden is the most logical choice. Why? Because it provides more space for plants for the exact same cost of fencing. This is what we mean by higher order thinking. We are not just calculating, we are using evidence from our data table to make an informed, optimal decision. It teaches students that in the real world, small logical adjustment can lead to much more efficient outcomes. The final step in our process is evaluation. This is where we verify if our heuristic actually works and if the solution is truly optimal. First, we double check the math. It is a simple but vital step. Does 9 plus 9 plus 9 plus 9 really equal to 36 meter? The answer is yes. So our perimeter constraint is respected. Next, we check for alternatives. We ask ourselves, can we make the garden even bigger? If we change the length or width by even 0.5 meters, for example 8.5 times 9.5, the area drops to 80.75 meters square. This confirms that our current solution is the peak of our investigation. Lastly, in a classroom setting, we compare with others. This encourages collaboration. By asking, did any other group find a larger area? We promote a culture of peer review and critical thinking. This evaluation phase ensures that our solution is not just a guess, it is a proven optimal result. After constructing our heuristic, we can see how computational thinking or CT truly supports non-routine problem solving through three key pillars. First, it provides a systematic approach. Without CT, students often get stuck in a trial and error guessing game. CT transforms this chaotic process into a systematic investigation. It gives students a clear starting point and a structured path to follow even when the problem feels messy or complex. Second, it fosters meaningful learning. Instead of just memorizing the area formula, students develop a deep conceptual understanding of the relationship between perimeter and the area. They see how changing one variable directly affects the outcome. This makes their learning experience more profound and long-lasting. Finally, CT is about efficiency. By using a well-constructed algorithm, we save time and energy. It ensures that students don't miss the optimal answer by accident. This efficiency is a critical skill in the modern world. Knowing how to find the best possible solution with the fewest possible steps. By integrating CT, we are not just solving a math problem, we are teaching students how to think like experts. Through this investigation, we arrive at several profound insights and new understandings. It is not just about getting the answer, it is about what we discover along the way. First is the mathematical insight. Students discover a powerful geometric truth that for a fixed perimeter, a square is the most efficient rectangle for maximizing area. This realization transforms their understanding of shapes from static figures into dynamic tools for efficiency. Second, we have the real-world discovery. We bridge the gap between the classroom and the industry. Students realize this game logic used daily. By packaging companies to save on cardboard, or by farmers who need to maximize their crop yield within a limited boundary. It makes mathematics feel alive and purposeful. Finally, we see cognitive growth. We are moving our students from simply calculating to optimizing. This is a key skill in the 21st century digital economy, where efficiency and strategic decision making are more valuable than basic arithmetic. We are teaching them that with logic they can achieve more with less. In this section, I want to highlight the role of digital tools in making our heuristic construction visible and engaging. First, I choose Canva as my primary visual tool. Beyond just slides, Canva allowed me to create a dynamic table and moving shapes. This is crucial because optimization is a process of change. By animating how the rectangle shifts, I can show exactly how the area responds to different dimensions in real time. Second, I adopted an infographic style. By using garden icons and fences, I aim to make this abstract mathematical problem more human and relatable. When students can visualize the physical context, they are more likely to stay engaged with the logic behind the numbers. Ultimately, my purpose here is to demonstrate that digital tools are not just for decoration. They are powerful communication instruments that can make complex, abstract heuristics easy to visualize and understand for any audience. It transforms a static lessons into an interactive learning experience. As I conclude my presentation, I would like to share some justification and reflection on the construction of this heuristic. First, regarding effectiveness, I believe this heuristic is highly successful because it provides a clear step-by-step algorithm. For a student, having a reliable recipe to follow removes the anxiety of facing a non-routine problem. It guarantees that if they follow the logic, they will find the best result every time. However, reflecting on the learning process, there is a main challenge. Notice that the abstraction phase can be tricky. Some students get so caught up in the context of garden, the plants, the soil, and the colors, that they lose sight of the mathematical constraints. As an educator, this tells me that my role is crucial in scaffolding their focus back to the core logic. Finally, the true value of this activity is that it develops flexible thinkers. We are not just teaching them to solve one specific garden problem, we are giving them a mindset. If the fancy material changes or the budget fluctuates tomorrow, they don't panic. They simply apply the same algorithm and CT components to the new situation. This is the essence of mathematical resilience. To wrap everything up, computational thinking is more than just a set of steps. It is the bridge that connects abstract mathematical theory to practical, the real world problem solving. Through this eco-friendly garden challenge, we have seen how logic can turn a limited resources into an optimized success. My final thought for today is this. By teaching our students how to construct their own heuristics, we are doing more than just helping them pass a math test. We are giving them the cognitive tools and the confidence to navigate any muddy or messy problem they are they will face in their future careers. Thank you very much for your time and attention.